Now let's do one example for Otto cycle. Here we have an air standard Otto cycle. What does air standard mean? If you say the word air standard, that means you can treat the gas inside the cylinder as air. In reality, it's not air. It's a mixture of a lot of different gases like CO2, CO, H2O. But if you see the word air standard, that means we assume the gas inside the cylinder is just air. So you can use air properties. And also because it is air, you can treat it as an ideal gas. Okay, and then what we know is pressure at the end of the combustion is 1 bar. So 1 bar, first of all, you have to identify P which one is equal to 1 bar. At the end of combustion, combustion process is 4 to 1. So the end of combustion is number 1. So P1 is equal to 1 bar. Make sure you understand which pressure it is talking about. And then the temperature at the end of heat loss process is 15 Celsius. So this is temperature which one? Heat loss is process 223 at the end, so that must be point number 3. T3 is 15 Celsius. And then in addition, we know compression ratio is gamma equal to 8. Since it is a ratio, it doesn't have a unit. And then Cp, specific heat at constant pressure is given. That is 718 joule per kilogram per Kelvin. K, the ratio of the two specific heats is 1.4. And combustion releases heat of 1000 kilojoule per kilogram. What we need to do first is to sketch the process on P versus nu and T versus S diagram. And then we next look for temperature at the end of combustion. At the end of combustion, 421 is combustion. At the end, so that's number 1. We're looking for T1. And then number 3 is to look for efficiency. Number 4 is to look for W cycle per unit mass. And number 5 is to look for heat loss per unit mass. Heat loss, which step is heat loss? That's process 223 per unit mass. Make sure you understand what the question asks for. Okay, so now let's start from part 1. Sketch the two diagrams. This is actually the easiest part of this example because if you have an Otto cycle, the two diagrams never change. Why? Because there's no phase change at all. Unlike before, there's no phase change. If there's no phase change, the two diagrams will always be the same. So you don't even need to justify anything or think about anything. You just copy what we did earlier. P versus nu and T versus S. On a P versus nu diagram, it's like this. 4 to 1, 1 to 2, isentropic, 2 to 3, 3 to 4, isentropic. And then on T versus S diagram, that's 4 to 1, constant volume. 1 to 2, isentropic, 2 to 3, constant volume. And 3 to 4, isentropic. So you don't need to think about anything. You just copy what we did before. Those two diagrams never change. Okay, so that's part 1. Part 2, we're looking for the temperature at the end of combustion, which is T1. Okay, we're looking for T1. What do we have? We have P1, which is 1 bar. We have T3, which is 15 Celsius. What else do we have? We have combustion releases heat of 1000 kilojoule per kilogram. So what is this? 1000 kilojoule per kilogram. What is this? This is the amount of heat released by combustion per unit mass. So now it should be what? Combustion process is 421, so it must be Q 421, and then per unit mass, so divided by mass. So this is 1000 and it should be Q421 per unit mass. This is what we have and we need to find T1. Let's start from Q421 because we do have an equation for that. Q421 per unit mass from first law, we know it's equal to U1 minus U4. And now let's recall, if it is ideal gas, you can actually calculate lowercase u instead of going to the tables. How do you calculate u? It's CV times T. And we always treat CV as a constant in this class. So now we take CV out of the two u's. What is left is T1 minus T4. Okay, so now do we have CV? We don't have CV. We have something really, really close. What is that? We have CP and K. Is it possible for us to find CV from CP and K? Yes. Let's recall. The definition of K is Cp over Cv. So from here, we can rewrite Cv into Cp over K. So now this equation becomes Cp over K times T1 minus T4. Since we're looking for T1, we will move T1 alone to the left-hand side and everything else to the other side. This equation becomes Q421 per unit mass times K over Cp and then plus T4. Let's take a look if we have everything in the right-hand side. First of all, Q421 per unit mass. This one, first term in the right-hand side, it's given. It's 1000 kilojoule per kilogram. Next one, K, given 1.4. Cp, given. T4, I don't have T4 yet. So if you can find T4, then T1 will be solved. How do we look for T4? Let's take a look. I have T3, and 3 to 4 is an isentropic process, so we do have an equation between number 3 and number 4. What is the equation? The equation is T4 over T3 equal to gamma K minus 1. And from here, we can find T4. That is T3 times gamma with the index of K minus 1. We plug in the numbers. T3 is 15 Celsius. Make sure you convert it to Kelvin by adding 273. Multiply by gamma. Gamma is compression ratio, which is 8, given. K is 1.4. So the solution for T4 is actually 661.5 Kelvin. So now I have T4. I can finally find T1. Okay, let's copy this equation again, and then what we do is just plug and chug. Okay, Q421 per unit mass is 1000 kilojoule per kilogram. So we multiply this number by 1000 to convert kilojoule to joule. The next one, K. K is given 1.4 divided by Cp. Cp is given 718 and it's SI unit. Plus T4, 661.5 Kelvin. So the solution for T1 is 2612 Kelvin. It must be SI unit Kelvin. So now I have T1, part 2 solved. And then part 3. Part 3 is to look for efficiency. And we do have an equation for efficiency. It's 1 minus 1 over gamma K minus 1. So we plug in the numbers. Gamma is 8, K is 1.4. The solution is 0.565. 56.5%, which doesn't look really high, but if you compare this number to previous vapor power system, which usually has a efficiency around 40%, you can see this efficiency is actually really high. And then part 4. Part 4 is to look for W cycle per unit mass, and we do have an equation for that. That is U1 minus U2 minus U4 minus U3. And then again, recall, lowercase u can be calculated by Cv times T if it is ideal gas. So we take Cv out of everything. What is left is T1 minus T2 minus T4 plus T3. And again, we rewrite CV. Recall the definition of K is Cp over Cv, so we can rewrite Cv into Cp over K just like before. So this equation becomes Cp over K times T1 minus T2 minus T4 plus T3. We do have Cp, it's given. We do have K. And T1, I just found it. T2, I don't have it yet. T4, what is T4? T4, yeah, actually we found T4. It's right here, 661.5 Kelvin. And T3 is given. So now you can see you just need to find T2. How do we look for T2? Recall, we do have an equation between 1 and 2 since it is isentropic. The equation is T2 over T1 equal to 1 over gamma K minus 1. So from here, I can find T2. T2 is equal to T1 divided by gamma K minus 1. Plug in the numbers. Solution for T2 is 1137 Kelvin. So now I have everything in the right hand side. I can easily find W cycle per unit mass. Plug in numbers. Cp is 718, K is 1.4 times T1 2612 minus T2 1137 minus T4 661.5 plus T3 15 Celsius. So convert it to Kelvin by adding 273. And then the final solution is 565 times 10 to the third. SI unit to the solution, joule per kilogram. So one more step, it's 565 kilojoule per kilogram. That is the solution to W cycle per unit mass. And then part 5. Part 5 is to look for heat loss. Heat loss is Q223 per unit mass. And from first law, we know it's U2 minus U3. We do the same thing, take CV out of it. What is left is T2 minus T3. And then rewrite CV to Cp over K, just like before. And we do have everything in the right-hand side. 718 over 1.4 times 1137 minus T3. T3 is 15 Celsius, so it's 288 Kelvin. And then the final solution is 435 times 10 to the third. The unit is joule per kilogram. Okay, and then we convert joule per kilogram to kilojoule per kilogram. So our solution is 435 kilojoule per kilogram.